In this web talk, I show how to use Mplus to do multi-step mixture modeling for latent transition analysis. This is joint work with Tiamar Asparahov. Multi-step mixture modeling concerns techniques commonly referred to as three-step, BCH, and two-step. The presentation illustrates several new Mplus features for these techniques that are included in Mplus version 9. Webtalk 10 is the third part of the trilogy of web talks on multi-step mixture modeling. Webtalk 8 discusses latent class analysis, and Webtalk 9 discusses new techniques to include direct effects for latent class analysis to capture measurement and non-invariance with respect to covariates. The extension to latent transition analysis in Webtalk 10 relates most closely to WebNote 21, but provides a much less technical account. It highlights Mplus syntax and special Mplus modeling features. Webtalk 10 assumes some knowledge of regular latent transition modeling using Mplus, that is, not using multi-step methods. Background for such regular latent transition modeling can be obtained from Webtalk 2. Analysis illustrations use simulated datasets that are available for practice. Key Mplus runs are included on the website of the talk. Here's the outline for the talk. We start with a reminder of a regular latent transition analysis, and then we turn to the multi-step area, where we're going to focus on distal outcomes and covariates, and with a special feature of missing data on the covariates. We're going to talk about the three common methods, three-step, BCH, and two-step, but with a special feature of imputations to handle the missing data on the covariates. We're going to take a look at the inputs in detail and the results. Then we turn to specific topics of LTA. We can take a look at transition-specific distal outcome means. We're interested in the transitions, so we may be interested in how the outcome means change for certain transitions over time. And we're going to introduce the so-called dot language, which turns out to be quite flexible. We're going to turn to the issue of empty cells and the problem of BCH failure in some context. Then we turn to multiple group LTA and the random intercept LTA. And then we end with latent class analysis at 2 time points and take a look at how that is different from LTA. Slide 3 shows a picture of a regular LTA with 2 time points, and we're going to consider binary indicators U1 through U12 here. So we have 2 latent class variables, C1 and C2, and we're interested in the influence of C1 on C2, also referred to as a transition. So the parameters in this model are number 1, indicator probabilities for each indicator U, where we have a probability for the indicator J referring to the number U1 in this case, conditional on class at a certain time point, CT. That is, the probability of this being 1 instead of 0 for class 1 and for class 2, etc. So those probabilities are showing the strength of relationship between the class and the indicator. And we in Mplus parameterize that as a threshold. Second, we have initial status probabilities, the probabilities of C1 here at the first time point. And then third, we have transition probabilities, that is probabilities of C2 classes given that we are in a certain C1 class. Now the indicators here can be of many different kinds: continuous, binary as we just talked about, ordered categorical, that is ordinal, or unordered categorical, that is nominal, or counts, or any combination of those. Now here we can also include covariates X in this picture, influencing C1 and C2. and study how covariates influence not only the initial status probabilities but also the transition probabilities. And we talk about that in Webtalk 2 on slides 58 to 64, where we also distinguish between effects of covariates on this transition that are main effects or interaction effects. So the main effect is that X influences C1 and influences C2. The interaction effect is that we have a C1 specific effect of X on C2. A C1 class specific effect of X on C2. Now, for a discussion of regular LTA, I refer to Mplus Webtalk 2, where this is described in detail. On slide 4, then, we have the input for Mplus analysis of a regular LTA. And we have this generated data set. At the end of the talk, I show the input for how this data set was generated. So it's simulated data for a sample size of 2,000, indicating that with the LTA, we do want to have larger sample sizes than we do typically for LCA. And we get an entropy measurement quality for both C1 and for C2 of a moderate level. Here are the names in the data set, and the variables that we're going to use are U1 through U12 here, and with this missing data flag. And we are going to specify 3 classes in each of the 2 latent class variables. And we declare U1 through U12 as categorical, and the program figures out that they are in fact binary. And we do mixture modeling with a moderate level of starts, 40 initial and 10 final analysis based on these perturbed random starting values. With LTA, you may want to, in general, increase that, maybe double it to 80-20. Slide 5 shows the input for regular latent transition analysis modeling part. And the modeling part has 3 pieces to it. One is the overall, the other is model C1, and the third one is model C2. So in the overall part here, then we say C2 regressed on C1. And that statement also produces several things. First of all, it produces the regression slopes, C2 sharp 1, class number 1 on C1, class number 1, C2 class 2 on C1 class 2, and etc. for the second row of C1, namely C2 number class 1 on C1 class 2, C2 class 2 on C1 class 2. So the first and the second row of the regressions. That's what C2 on C1 implies, but it also implies these values for C1 and C2. So C1 class 1 and C1 class 2, those are the initial status logits producing the initial status probabilities. C2 class 1, C2 class 2, they produce the intercepts in the regression of C2 on C1. You can explicitly say these things in the model. You would have to put brackets around them because they are level related parameters. This is a mean, this is an intercept, to talk in continuous variable terms. And here are the 4 slopes. You see this discussed in detail in Webtalk 2, but also at the end of chapter 14 of the user's guide, which describes the logit parameterization. But Webtalk 2 gives more detail to it. So that's the first part, conveniently summarized in this statement, but you should be aware that it produces 4 slopes and a couple of means and a couple of intercepts. Now, model C1 then has the thresholds for the 6 latent class indicators at each of the 3 C1 classes. So that refers then to the first part of the modeling parameters that we showed in the picture, whereas the other parts are in the initial status and the transition parts of the model. Model C2 then, well, we repeat the same structure here, but we start then with U7, the second time indicators, 7 through 12, for each of the three classes. And we're going to use equality constraints. You see that first class 1 through 6, first class 1 through 6, same parameter values. We hold them equal across time. Because we're thinking about this, and the same for the other classes. And we're thinking about this as a typical LTE application, where U7 through U12 are the same measures as U1 through U6. Same measures, same variables, but recorded at time 2. And to make sure that we capture the same latent class construct at the 2 time points, we want to specify measurement invariance across time by these equality constraints expressed by these parameter labels that we have given here. Now, it may not hold exactly perfectly, and you may want to look for deviation from that full measurement invariance, and I discussed that in Webtalk too. But that may well be your baseline assumption that you would start out with. On slide 6, we see a very useful piece of output that gives latent class indicator probabilities. Here we give them for C1. It's the same for C2. Same probabilities for the 2 time points due to the measurement invariance that we specified. So you have the 6 indicators here. In this case, it's U1 through U6 because we're talking about C1, but it's the same for U7 through U12. You have the 3 latent classes as columns, and we look at the highest category, which is U1 equals 1 as opposed to 0, but we number the categories as 1 and 2. And you see then that class 1 consists of people who have a high probability of saying that they do whatever U1 involves. High probability of U1 equals 1 for all the U's. So that's the high class. Second class is low, 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 high, high, high. So it's a low, high class. And the third class is a low, 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 low. Low for all items. And in this case, class 3 turns out to be the most frequent. So that's the normative class, having a low probability of engaging in whatever behavior the U's refer to. So slide 7 then gives the latent transition results. We have, first of all, the latent class probabilities for the starting point at time 1 and for time 2. The latent transition probabilities based on the estimated model is what we're primarily focused on here. So the rows are the 3 classes of C1 and the columns, the 3 classes of C2. So for people who start in C1 class number 1, that is being in the first row, they have a probability of 0.483 to stay in class 1 at time point 2, and lower probabilities to move to other classes at time point 2. Same thing for class 2, where the probability is the highest to move to class 3. Typically we have higher values on the diagonal. Some kind of inertia is often seen, and that's seen for the third row, where the highest probability is staying in class 3. What we want to do here is look at this in another metric as well, transition probability odds. So at the bottom here of the slide, you have a table where the diagonal has 1. So what we're doing is we're looking at the odds of moving to another class at time 2 versus staying in the class that you began at. So we're comparing to staying in the same class. So the value 0.474 here is simply obtained as 0.229 divided by 0.483. So we're comparing probabilities in an odds metric, so a ratio of probabilities. And we see that that's less than 1. And we can look at the confidence interval, which takes into account non-symmetry, as it should. And so it's a non-symmetric confidence interval. And it does not include 1, which says that 0.474, that odds, is significantly less than 1. So it's significantly less than the 1 odds here, which says essentially that the probability of moving to class 2, 0.229, is significantly lower than 0.483 in the odds metric. The odds for the moving to class 3 versus staying in class 1 is a little bit higher, because that probability is a little bit higher. So the key question is if the confidence interval includes 1, making it insignificant, versus not including 1. And the odds can be either smaller than 1 or greater than 1. With x's included in the model, we also have transition probability odds ratios, because then we're talking about 2 variables. Odds refer to one variable, C2 for being in class 2 versus class 1, but with an x variable we have 2 variables, and we can see the effect on the transition probabilities in terms of odds ratios as a function of each of the x variables. So that's not available or not used here because we don't have any covariates. On slide 8, I turn to the main topic of multi-step LTA, where we add distal outcomes and covariates to the basic LTA measurement model, with a special feature that we're going to consider missing data on the covariates. And we're going to talk about 3 different methods in the context of using imputation for the covariates with missing data. Slide 9 shows the model. So we have the 6 latent class indicators at time 1 and the 6 indicators at time 2. And now we add a set of distal outcomes out here, y, and we also add a set of covariates, x, down here. So we have a combination of different kinds of covariates. x1 is binary, x2 through x3 are continuous, and we have missing data on x1 and x2, but not on x3. The distal outcomes are also of different kinds. y1 is binary, y2 is ordinal, and y3 is continuous. And we have no missing data on these y's for simplicity here. And note that we specified that it's C2 that influences the distal outcomes, not C1, nor a combination of C1 and C2 influencing the y's. We're going to talk about those topics towards the end of this web talk. But it's natural to think that the last time point of the LTA is what's relevant for predicting a distal outcome. Now note also that there's no interaction between C1 and X in their influence on C2. So you can portray this as the influence of X on C2 does not vary across the C1 classes. And in Webtalk 2, where we talk about LTA, in the non-multi-step approach, we refer to that as the main effect model. No interaction between C1 and X in the influencing C2. Main effect model as opposed to the interaction model. And I would argue that in most cases the main effect model is sufficient. I see many applications from Mplus users with the interaction, and perhaps we're guilty because our user's guide examples featured such interactions, but we just wanted to show the full generality, not necessarily what we recommend in any given application. So now note also that C2 and X do not interact in their influence on the y's. So the regression of y on x is not C2 specific. So that's what we talked about in Webtalk 8 for latent class analysis. So you just consider this part of the model down here, well, with the indicators too. So there's no interaction between, in the influence of x on y, it's not C2 specific, but there's only a main effect of C2 on y and an main effect from x to y as well. Now the measurement model is what we refer to as this part. So we have 12 indicators total of 2 latent class variables. And now we're going to add to that measurement model the distal outcomes and the covariates. So the multi-step idea here is that the covariates and the distal outcomes should not affect the measurement part of the model, should not affect the formation of these 2 latent class variables. And we talked about the multi-step rationale in Webtalk 8 about LCA with a single latent class variable, claiming that there is a need to separate the estimation of the measurement model from the full model adding then the distals and the covariates, so the latent classes don't change. And that's with respect to both distal outcomes and covariates. Distal outcomes in the full model, that is adding the y's after time point 2 in this case, they may be measured later in time than the variables of the measurement model. And you want to predict from a measurement model using the information you have at that time point. And the covariates in the full model may also affect the latent class enumeration. And if you go back and forth between different set of covariates, you would have to, in principle, redo the latent class enumeration. So you want to separate the estimation of the measurement model from the full model. And that is what's done by multi-step approaches. The first step, the latent classes are determined only by the measurement model. And the last step, distal outcomes and or covariates of the full model are added. And the theory for this multi-step approach is described in the statistics methodology section of Webtalk 8 on LCA. Now we're going to talk about 3 approaches, 3-step, BCH, and 2-step. And for 3-step, we're talking about what's sometimes referred to as maximum likelihood 3-step. BCH in some literature is also referred to as 3-step, but we think of that only simply as BCH. So 3-step and the BCH approaches use the posterior probabilities from the estimated measurement model to determine each individual's most likely class membership and take its measurement error into account. And we describe that in detail in Webtalk 8. So in 3-step, the last step then uses fixed loaded values from the measurement model to take measurement error into account in the most likely class classification. For BCH instead, we use weights from the measurement model to take measurement error into account in this most likely class classification. 2-step takes a quite different approach. Last step uses fixed measurement model parameters to avoid measurement error in this last step. So that's an interesting newcomer to the methods arsenal. Slide 12 then. What about studies of multi-step approaches for LTA? Well, surprisingly, there are rather few, it seems. I may be overlooking some papers or some recent results. But there are simulations in our web note 15 and 21 that Timur Asparahov and I did. And we looked at covariate setting for LTA 3-step in web note 15. Seemed to work okay. And BCH was looked at for covariates in web note 21. Also looked okay. For distal outcomes, we looked at simulations for BCH in web note 21. and we find that BCH does better than two-step when distal outcomes are non-normal within class. But there's so much more that could be studied here for multi-step LTA. And note then, if you're interested in that two-step is harder to study, as it says here, because logistically, for each replication, the parameter values need to be changed. Now we're going to take a look at the special case of this, where you have missing data on the covariates used in the last step analysis. And that's where imputation comes into play, as I was mentioning. On slide 13, I list the various multi-step approaches that you can use with missing data on X in the last step analysis. You can bring covariates into the model, or you can do multiple imputation. Those are the two main approaches. Bringing them into the model, which is explained in detail in Webtalk 8, can use either maximum likelihood or Bayes. With maximum likelihood, you need to do numerical integration, and you can use three-step for that. BCH is not available with numerical integration in this last step. It is available in the first step, as we will see towards the end of this talk when we talk about RI LTA, random intercept LTA. Two-step works as well. So the advantage here of ML is, of course, that we have likelihood ratio testing. And then the disadvantage is that you have a hard time handling many covariates with missing. It can be somewhat unstable with large amounts of missing data, and can be imprecise without many integration points. And we cannot specify that the covariates are categorical when that is the case. Remember the binary x1 variable. Alternatively, instead of ML, you can use Bayes. You can use three-step. You cannot use BCH because that's not available due to the weights. We don't have weights in Bayes. And you can also use two-step. The advantage is it's stable, perhaps more so than the ML. And the disadvantage is no likelihood ratio testing. Can be slow, cannot specify categorical covariates either. We're going to focus on the alternative of multiple imputation of the covariates X in the last step analysis. And in that case, we have all three methods available. And the advantage is that that's a stable analysis. You can specify categorical covariates, and you can also use non-model variables for missing data imputation. That is, variables that are not part of the model, but nevertheless can be contributing useful information for the missing data imputation. And the disadvantage is then that we don't have the likelihood ratio testing worked out for the multiple imputation approach, and it can be slow with many covariates that have missing. So if you don't have a lot of missing, you may not want to get into these methods at all. Now, the corresponding LCA approaches were discussed in Mplus Webtalk 8. So now, one comment here regarding BCH on slide 14 to pay attention to. The BCH weight computations in the first step require attention. Webtalk 8 discusses BCH weights for LCA with one latent class variable, that is. Now for LTA, you get the BCH weights as the product of weights for each time point, as if you were estimating them separately. Now we don't have to estimate them separately. We can do a joint analysis of all time points and obtain a separation of the time points in the estimation by not regressing C on C, that is C2 on C1 in this case. Because then the weights for each time point can be automatically or are automatically multiplied together to create weights for all time points. So you do an analysis of time 1 and time 2, U1 through U12, and you get the weights automatically created in the right way if you do not have C2 on C1. So in the first step analysis, you do not include C on C, but in the last step you do. And in Web Note 21, Tiermer did some nice simulation studies to see that that's the way to go. The first step and the last step, handling of C on C. And this idea of not including and including agrees with this paper by Susa Back, Teckley, and Vermont from 2013 on these 2 pages. So now we turn to the actual Mplus inputs, and we'll take a look at the results of the analysis using these different approaches. Slide 16 shows a useful summary of the different steps, and this is then geared towards handling missing data on the covariates. And we're going to talk about 2 stages of analysis: the measurement model stage and the final analysis stage. I'm using the word stage instead of steps here, not to mix it up with 3-step and 2-step, by keeping it in 2 parts here. So first stage is the measurement model analysis, and input specifications then that we should pay attention to include the use variables list, which is then the U1 through U12 latent class indicators. And on the right, in the right column here, you have the variables that are saved in the analysis when you add the save data command. So when you have the save data command, you automatically save the use variable, the variables on the use variable list. Now in the first stage, we also want to ask for auxiliary, the auxiliary option for saving variables for the final stage. So the variables that we would save then are the covariates and the distal outcomes. Furthermore, you want to use the save data command to save C probabilities, which are used for 3-step. That saves the C probabilities for the 9 combinations of classes, 3 times 3. And we also have N1 and N2, which are the words we used for the most likely classes for time point 1 and time point 2. We use the letter N for referring to a nominal variable. The save data command you can also use to save BCH weights for the BCH multi-step approach, and that saves the weights, the BCH weights for the 9 class combinations in the saved data. And then you also want to use S values, which is for S2-step, and that's not variables saved, but they will come out in the output from the stage A measurement model analysis, and you will then be able to copy those into the second stage, which is the final analysis, including multiple imputation first of all for the X's with missing data, and then an analysis of the full model meaning that we add the covariates and the distal outcomes. And we're going to use data imputation for missing on X. Can be replaced by integration, but we're going to focus on imputation for missing on X here. And then in the final analysis here, stage B, we have the alternatives, 3-step, BCH, and 2-step. And the way you've set it up then here means that you can easily do all 3 if you want to. And let's take a look at the difference between the 3 approaches. For 3-step, the use variable list includes the most likely classes designation, N1 and N2 for the C1 and C2 latent class variables, and then the covariates and distal outcomes. For BCH, the use variable list does not include N1 N2, but X1 and Y3, X1 to X3 and Y1 to Y3. And for 2-step, the use variable list includes the measurement model indicators U1 through U12, because we fixed those measurement parameters, as well as the covariates and the distal outcomes. For 3-step then, we have to also look at the logits from stage A and copy those logits into the last step, manually added. BCH, however, has the convenience that you get the BCH weights in the first step, in the stage A rather, and in the stage B analysis, you only have to specify that this training option, W1 through W9, in parentheses BCH. So that's the most convenient approach for taking these two stages of analysis. For two-step, you have to copy over the S values from stage A and manually adding to them to the input for the stage B analysis, and change the asterisks to @ to fix those values, as we discussed in detail in Webtalk 8. So there you have a summary of it. So let's take a look at the details of the input then for stage A on slide 17. So here we save the information we need for the final analysis. So we have this data set, LTA distal N2K, same data set as we use for the regular LTA analysis. And here's a list of variables in that data set. And we're going to use the latent class indicators, U1 through U12. And we're going to have 3 classes for each time point and declare those U variables as categorical. And here's what we need to do. We need to add the auxiliary option to save X's and Y's for the last step. And then we do a mixture analysis with a sufficient number of starts. And continuing on the next slide, then we have the model parts, the overall model, model C1 and model C2. And the overall part, then we don't say C2 on C1, but leave that at 0, as we have discussed earlier. And for model C1, we have the 3 classes of C1 with labels to be able to hold equalities across time for the same indicators at time point 2. And then we save the data, use the save data command to save the C probabilities for 3-step, BCH weights for BCH, and we save them in the stage A.dat, the new data set. And we also ask for S values, so we get those ready if we want to try 2-step analysis. And here's what we get: latent class counts and proportions for each variable, C1 and C2. And you get a 0.42 class, 27, 28, 298 here, and a little bit different at the second time point, because there are transitions from C1 to C2 that creates a different marginal distribution for C2. So that's all right. Now we may want to reorder the classes. Typically we want to have the biggest class last, because that's the class we compare to. So for ease of interpretation, we may want to put that normative class last. It doesn't matter to the, doesn't change the analysis results, except maybe more easily interpretable. So we can reorder the classes, and we want to do that in this first stage. So based on C1 here, we want to have the lowest class first, say. So 2 comes first, and then the second lowest comes next, so 3, and the biggest class we want to have last. And we want to do the same thing for C2. So 231 bar 231. So reordering of the classes is easily done. You have the same input here as before, except now you have opt seed. You take the optimal seed from the output in the first run, and here is the same input as before, except you have added then the S values reordering. All right, slide 22 then. Let's take a look at something here which might be of interest. I'm specifying the latent class indicator probabilities. You know, we talked about a high class, a low high class, and a low class. And that was from regular LTA, where we do specify C on C, so to speak, C2 on C1. And comparing that then to the first step or stage A, of the multi-step analysis, where we have no C on C, you see that in this case, the two solutions for the measurement model are very much the same, very similar. 794, 793, 786, 787, etc. And now in this case, they're similar because the data are generated to fit the model, a model exactly like this, whereas in real data, you may have a discrepancy between these two. This analysis on the right here is like analyzing each time point separately, whereas this analysis on the left looks at the joint analysis of both time points, and they may come out differently. For instance, if you have some correlations across time between indicators that are not accounted for by the regression of C on C. So you may want to keep an eye on that in your real analysis. Now, stage B then, on slide 23, what does that do? Okay, so we have the last step of 3-step here first. I'm going to do all three methods, 3-step, BCH, and 2-step. And it's based on the reordering of the classes. So stage A data has been saved in this reordered run, where we have the biggest class last. And here is the variable list that comes out of the stage A output. So the variables in stage A are listed at the end of that stage A run. And since it's 3-step, we're going to have the use variable list that includes these nominal variables, most likely class variables for C1 and C2, and then the covariates and the distals. And the categorical variables here then are Y1 and Y2. Y3 was continuous. And nominal is what we use for N1 and N2. And in stage A, the missing data flag is no longer 999, but it's asterisk. Now we're going to do the data imputation step here within this stage B analysis. So we do data imputation for the axis, and I'll describe that in some detail in Webtalk 8. But essentially, here's how it works. You have a names list. That's a set of variables that you use to inform about the imputation. So they carry information that's useful in imputing. And what do we impute? We impute x1 and x2, the two missing x's. So we specify what kind of variables they are, categorical for U1, U12, and for x1, and for y1 and y2. And we impute x1 and x2, and x1 is imputed as categorical, in this case binary. So here's the imputation approach that actually does take into account that x1 is binary. Again, I talk more about that in Webtalk 8. And we're going to impute 100 data sets. We're going to draw 100 plausible values imputation for to get 100 data sets which have observed information on x1 and x2 by imputation. And we're going to save that as imputed asterisk.dat, so a list of data sets. And this imputation is done by Bayesian analysis. So we have the concept of thinning, that is not saving every iteration in the Bayes analysis, but skipping to make observations more independent. And we do thinning equals 100, that may be more than we need. Anyway, so we do mixture analysis then on these data, and although we use Bayes here for imputation, our analysis estimator is maximum likelihood. And since it's the last stage, the last step, we use starts equals 0. So on slide 24 then, the last step of 3-step is as follows. You have then C2 on C1 here, and you have C1 through C2 on the covariates, and Y1 through Y3 on the covariates as well. And note then that in this case, at this stage, there's no missing on X after imputation. So they are treated as regular observed covariates that we condition on in the regression. No need to bring them into the model to handle the missing data, because there's no missing data on them, on the axis, after the imputation stage, shown on the previous slide. I shouldn't call it stage, but after the imputation within stage B. So one analysis here that does imputation and mixture modeling in one single run. And then you have model C1 and model C2, where, because it's three-step, we fix these loadeds. These loadeds come from the stage A analysis that we copy over like this and fix them. And you can, if you want, add Tech 8 in the output, which shows you the base imputation iterations. Usually they come out okay, and you don't have to worry about them. Now these loaded values, like I said, they are found for each latent class variable in stage A. So each latent class variable, C1 and C2, have these fixed loadeds. On slide 25, we turn to using the BCH method in the stage B, that is the last step, based on that reordering we did in the first stage, stage A. All right, so we still use the stage A data set, with these variables in the data. And now the use variable list does not include N1 and N2, but only the X's and the Y's. And declare the two Y's as categorical here. And now we add training, the training option, BCH. We have the same data imputation statement as for three-step. And the analysis by ML here is the same, except we don't have to bother with the fixed loadeds. All we do is specify the overall model as we did for three-step, and then model C2. And we don't have to bother with model C1 because we have the training weights. And all we have to do is to say that the distal outcomes vary as a function of C2 alone here. So the thresholds and means are mentioned in each of the three C2 classes to match the picture, the figure of the model, where C2 influences the distal outcomes, but C1 does not. The X's, again, they come in the regressions here, and once again, there's no missing on them because we've already done imputation. All right, slide 26 then. What about two-step in stage B? All right, the stage A data is the same. Alternatively, two-step can use the original data, since most likely class and weights are not needed, so we don't have to save that extra stage A that data set if you don't want to. So the use variables then are including the latent class indicators, because that's the measurement model part that we want to fix the parameters of using two-step, and then the X's and the Y's. So we include on the categorical list then the U variables as well, in addition to Y1 and Y2. Data imputation is the same as before. Mixture modeling is the same. Starts equals 0 because it's the last step. And two-step then continues here with C2 on C1 and C on X and Y on X. And in addition then now we have to use model C1, fixing the measurement parameters here using ampersand, having changed the asterisk to ampersand by copying the S value output in the first stage and changing the asterisk to ampersand. And same for C1 class 2 and 3, and on the next slide 28 for model C2, fixing those measurement parameter values. And again for model C2 we specify the thresholds and means for the Y's, because C2 is the only variable that influences the distal outcomes. So that's pretty straightforward. Again, least amount of work is required by BCH. And however, BCH doesn't always work, so we have to be aware of the other methods. Slide 29 gives the latent transition analysis class probabilities for the different approaches. As a comparison, we also give the class probabilities for the regular LTA, and we can compare that to the stage A of the multi-step approach. And to remind you, the regular LTA does allow for C2 on C1 regression, whereas stage A of the multi-step approach does not. And you see that in this case, the differences are very small between those two approaches. What we really want to focus on, though, is the difference between the stage A class probabilities and that are obtained from what we call the measurement model, and the multi-step methods, the 3 multi-step methods in stage B that add covariates and distal outcomes. And we see that we have fairly good control, or very good control, of the class probabilities between the first and the last stages in all cases. In fact, for the BCH approach, it's right on target, apart from this little difference here. And very close values, and here exactly the same as stage A. 2-step is also very, very close. So that's something you may want to check in your real data analysis. Slide 30 shows the LTA results for BCH. You have the class probabilities up at the top, but that we looked at before. And here I'm presenting also the estimated, some of the estimated quantities in the output. And I distinguish between 4 different parts of the output: the influence of X on C2, I'm ignoring X on C1, the influence of X on the Y's, and I'm only looking at Y1 and Y3, the influence of C1 on C2, and the influence of C2 on Y. So where you find these pieces of output in the Mplus run that you do is described in Webtalk 8 in detail. Now, I have this for both BCH and for, on the next slide, for 2-step, and you will find that the results are fairly similar. So for instance, if you look at the Y1 odds ratios, influence of X on Y, 1.806, etc. If you go back to slide 30, 1.885, 578, 502, back to slide 31, fairly close. In fact, all the numbers are very close to each other across the 2 methods. I have not presented 3-step here. And the asterisk, the significance, the estimates that are significant are the same except for one. This influence of X3 on the C2 class 2 odds ratio is significant here for 2-step, but not for BCH. It's also not significant for 3-step. So the significance for 2-step is therefore slightly suspect. And that's perhaps, although this is one observation, one data set, one replication in the Monte Carlo study, may be indicative of the fact that the 2-step standard errors are slightly underestimated due to not taking into account the random variation in the measurement parameters. Usually doesn't make much of a difference, and here actually the confidence intervals are very similar. It just slips over into significance for 2-step, whereas it was not for BCH nor for 3-step. On slide 32, we turn to LTA with transition-specific distal outcome means, introducing the so-called dot language. So if you look at this picture again, that we used for a multi-step LTA, where we have the measurement part up here, distal outcomes out here, and covariates down here. Let's remind ourselves what this picture means. So it specifies that C2 influences Y. C2 influences the Y, the distal outcomes, and they're not influenced by C1. So to handle that, we used Y parameters that we mentioned in the model C2 classes to let them vary across the C2 classes. And that specification then implies that the Y parameters are held equal across the C1 classes. So when we say that they vary across C2 classes, we implicitly also say that they're held equal across C1 classes. Otherwise, they would be influenced by C1 as well. Now, Y parameters not mentioned in model C1 or model C2 classes implies that the means and thresholds for the distal outcomes Y vary across all combinations of the C1, C2 classes by default. So what if you wanted something in between of those two extremes? Well, let's look at slide 34. We introduced the dot language, and in this case we want a distal mean or a threshold specific to one specific LTA transition. Now the Y parameters then mentioned in model C2 and in a specific class combination, which corresponds to a certain transition pattern, can be specified using the dot language. So for instance here, C1 class number 2 dot C2 class number 3 can have a specific distal outcome mean or threshold, a certain transition pattern that we're interested in, and to see if that has a special effect on the distal outcomes. And that dot specification overrides the Y parameter equalities across the C1 classes that was implied by specifying that they vary across model C2 classes. And syntax for that is as follows. The dot specification can be placed in the overall subsection of the model or below the model C2 under a new model command section. We're going to take the first alternative here. So slide 35 then, let's take a look at how two-step analysis deals with this. So we have the stage A analysis here using two-step, where the used variable list is like this, including the indicators. And we do data imputation just like before. And nothing is new on this slide so far. What's new comes on slide 36, where in addition to this overall statement, we also add a class combination specific statement. So let the transition from class 2 to class 3 have a specific distal mean and threshold. C1 sharp 2 dot C2 sharp 3. And then we give in brackets those intercepts or means and thresholds. So that's how you do this specific transition pattern influence on the distals. And then the rest is just standard two-step. We fix the measurement parameters here on slide 36 and continue on slide 37, where, as before, we have the effect of model C2, effect of C2 on the distals in each of the classes. But we also allow on slide 36, going back one, to have a specific effect from this transition. So no longer are the thresholds and means the same across all of the C1 classes, as an effect from C2 would imply, but we let the second class of C2 in combination with the third class of C1, did I say that right? The second class of C1 in combination with the third class of C2, let that have a specific threshold mean. So no longer equal to, in this case, specifically the other C1 classes. All right, so then we take one step further on this dot topic. Slide 38. What if we want distal means and threshold specific to all LTA transitions? Well, we can draw it like this. So the influence of C2 on the distals, I brought the distals down from up here to down below here for the simplicity of the figure. And we're saying that the influence of C2 on the y's is also influenced by C1. So it's a C1, C2 interaction here with these broken arrows. Should be broken arrows everywhere. That, well, it should be broken arrows 1, 2, 3. There are 3 broken arrows, yes, and then the direct effect from C1 as well. Main effect, one can call it. Now in this case, we said that we could just not mention the distal outcome means and thresholds, and they would all be different across all the classes, all the class combinations. That's true, but we may want to explicitly say this for the following reason that I will make clear on the next slide. This is a new data set here with the distal outcomes. Y1 is continuous, Y2 binary, Y3 ordinal. I call it LTA distal N to K dot on slide 39. So we do 3-step here. We mix things up a little bit, varying the 3-step with 2-step and BCH. And we have done a previous run, and we want to do a reordering using S values, as you see bottom right here. And we have the opposite for that, to do that. And no C2 on C1 in the first step as before. And we have measurement equalities across time, and we save the C probabilities in C prob dot dat data set. And off we go into the last step of 3-step using this dot language. So the file is cprob dot dat, and we have on the use variable list the most likely class memberships, C1 and C2 in the nominal variables. And you have C2 on C1. So the new interesting thing here is that you have the dot language specification here then for each combination, C1, so it's 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. And give the means, means and threshold for that. There are no covariates here, so there are means for the continuous. But we also can give the labels here. That's not necessary to do, but we want to give that here because probably you will be interested in looking at differences between different transitions, different rows here, in terms of, say, the mean of Y1. Is the Y1 mean different between this transition as compared to this other transition? And to do that, you have to have parameter labels that you then use in the mod constraint statement to create a difference between the two and estimate that difference and get a standard error automatically by the delta method for that to get a test of whether that difference is significant. And since it's 3-step, we also have to have the fixed logits in the input, as just like before. Now we turn to the topic of empty cells. So we're going to consider a new data set. On slide 43, I mentioned that it's an LTA with empty cells for the latent classes and n equal to 2000 still. But here we now have 4 classes at both time points. And we're going to take a look at distal outcome means estimated as influenced by C2 again. First, let's consider regular LTA, so no covariates, no distal outcomes, that is not doing a multi-step analysis. So in that case, we do regress C2 on C1. And we're going to impose measurement invariance. So we have the same labels here at the time point 1 and time point 2 for all of the classes. In this case, as shown on slide 45, the empty cells results in a lot of error messages. Here is what you see. The standard errors or model parameters may not be trustworthy. Non-positive definite first-order derivative matrix. That first-order derivative matrix is what we also refer to as something produced by the MLF, F as in Frank, or first-order version of maximum likelihood estimation. Special way to compute the standard errors. That's very sensitive to, or the most sensitive version to catch problems like this. So we see a problem here. C2 class 1 regressed on C1 class 3 has a problem. Condition number is very small, minus 16 to the power of minus 16 is a very small number, close to 0. But we also get a new message here that value, that estimate, does not affect the data fit in the range of parameter it is in. So that essentially says that it's not identified, and turns out it's not identified because the cell is empty. We also have another error message for C23 on C11, and there we get the message due to a singular information matrix. So that has to do with the standard errors, the maximum likelihood standard errors. And all of this is described in detail in Webtalk 2 in the context of error messages, described in segments 21 and 22. So the first error message is not fixed by Mplus, but flagged by the so-called MLF information matrix check up here, top message, suggesting that you might fix it at the value estimated or just ignore it. It can't be estimated. C, the other one is fixed based on the ML information check. So here's what the output looks like. So the first one, the first problem we had, it's a big value, but it's not fixed. You can tell that it's not fixed because when it's fixed, you would have 999 here, which you get for the other error message, a very large negative value here. It's fixed at that value, but that one is not fixed. But neither one of these two can be estimated, really. And here I'm just repeating the sentences at the previous slide. So what does that correspond to? Well, you can take a look at the joint latent class probabilities table. So you have all of the, in this case, 4 times 4, 16 patterns here. And pattern 1, 3, being in class 1 at time point 1 and class 3 at time point 2, has nobody in it. Same thing for class 3, 1. And when the joint probability has a 0, this little formula below here implies that the transition probability is also 0. Don't have to bother with that if you're not interested in these technicalities rather. But in the transition probability table then, still for this regular LTA, you have then the zeros showing up in these two spots. And you may wonder, why does it show up for 4 and not for 3? Because after all, it was in 1, 3. Well, it shows up in the last one that precedes the 0. Anyway, there are 2 zeros here, and those zeros can create problems. Let's see. When we now move to multi-step analysis, so now we have multi-step analysis, adding the distal outcome, and let's look at the first step here. So we do the latent class indicators, and we have the invariance across time as before, and we open up for the possibility of using all 3 methods by asking for C-probs for 3-step and BCH weights for BCH, and S values for 2-step. Now, here we are still in the first step, but we want to reorder the classes to agree with the LTA analysis without distal, just for comparison purposes for this talk. So we have an S values reordering here, and we have an op seed from that first run. Otherwise, things are the same here. Slide 52. multi-step analysis using BCH. So here we take a look at the BCH estimator in the last step. And we then have the use variables are y, and the weight variables, you don't have to mention the weight variables if you don't want to. They just get dropped off from the model automatically. They're not part of the analysis. They only appear in the training statement. And then we have C2 on C1 here in the last step, of course. And we have the distal outcome, the continuous variable mean for y. And in that case then, using BCH, the latent transition probabilities have yet another zero, which is compared to slide 48, which was for regular LTA. The cell 1,4 has gone from 0.019 to 0 here. Close. But we have now 3 zeros. And we can take a look then at the latent class probabilities for the last step of BCH. Here they are for C1 and C2, and compare to the first step. And we see then that we have a little bit more difference than we've seen before. 0.213 versus 0.250. This one, 0.213, is smaller than 0.250, whereas here it's the reverse, not by much, but still, there seem to be a little bit bigger differences, and BCH doesn't do as well here, it looks like, in this single analysis. And in that case, you may want to contemplate trying out two-step analysis and see how that works. Now, this is related then to a topic that's shown here on slide 53 called BCH failure, which can happen with empty cells. So on slide 54 then, I make some statements about BCH weights. They can be negative, and that's fine. They should sum to 1 over class for each individual. They typically do. But they should not sum to a negative value over individuals for any class. So if you think of adding the weights down the rows in any specific column, they should not add to a negative value. Because if it does, that can prevent convergence. And you get a fatal error stoppage due to total negative weight, and BCH fails. You have to choose one of the other two, multi-step method. But if convergence occurs, the solution is okay. And this can happen with empty cells, but also with small class sizes and low entropy. And the example is distal outcome means varying across all transition patterns with empty cells. So you have these not identification issues. So the solutions to BCH weight problems, where you have no solution to the failure due to total negative weight. But if you have continuous distal outcomes, you can estimate, instead of having the estimated negative variances, which can happen, you hold variances equal across classes, which is the default of Mplus anyway. But if you specify them as unequal, some of them may turn out negative. To avoid that, you can hold them equal across classes again. You can also have the problem of estimated negative frequencies for categorical distal outcomes. You don't want negative frequencies. So in that case, you may want to hold probabilities equal across certain classes to avoid that. Or you can use another multi-step method such as two-step. Slide 55 then. Let's take a look at the last step of BCH using the dot language once again. So distal outcome means varying across all transition patterns. So you have training BCH here, and you have all of the 4x4 combinations of classes, and you have the Y mean estimated freely in all of them. Slide 56 then shows the error messages that we get in this case. We got a problem with the estimated covariance matrix for Y. not positive definite in class 1. Couldn't complete the computations in iteration 2. Maybe due to 0 estimated variance, no within class variation for the variable. Of course, there's nobody there, for instance. Here are suggestions. The warning is due to negative variance, residual variance. Avoid specifying, here's one thing, avoid specifying class invariant covariance when the corresponding variances are not specified as class invariant. That combination doesn't make sense, so we shouldn't do that. But the real error here is the fatal error again. The fatal error for the total BCH weight for class pattern 1, 2 is negative. This is likely an empty class. The BCH model estimation could not be completed. So, BCH failure. Slide 57 then. We repeat that the fatal error, total BCH weight for class pattern 1, 2 is negative. That's what we said on the last slide, right? Yes, but down here. Slide 57, negative minus 8 point something, likely an empty class. So if you want to look at that, you can actually look at the weights that you save from the first step, the BCH weights. You can do the sample statistics on them, on the weights. You can look at the means. And you see then that you have a negative mean here in the for the second weight, and the second weight corresponds to pattern 1, 2. You know, first weight is 1, 1, second is 1, 2, and this is 1, 3. So you have negative 0.004, and that is the weight, the mean of the weight times the number of people in the total sample gives you minus 8.662. So you can see that the total weight is indeed negative as stated. So BCH fails here due to empty classes and estimating means for classes that have nobody in them. And therefore you may want to switch over to two-step analysis. We're now ready to turn to multiple group LTA. Slide 59 then. We're going to use the same data set as before early on in this talk for multi-step analysis. We're going to treat the binary x1 variable as a group variable. You know, could be male female, for instance. And we can do that by specifying x1 as a perfect indicator. I'm going to say what that means, of a new latent class variable C in addition to C1 and C2. Sometimes you can specify groups as known class in mixture modeling, but that's not allowed with BCH training variables. So we take this tack instead. And that's a good approach that can be combined with 1-step, 2-step, 3-step, and BCH with or without imputation of missing data on X's. And you can get quite a lot of model flexibility using the dot language, specifying particular combinations of latent classes. So where you bring in C and C1, C2. And where any parameter across these dot commands can be different or held equal across any combinations of latent classes. On slide 60 then, we first take a look at multiple group analysis for regular LTA, so not multi-step yet. So we have these class variables C with two classes corresponding to x1, as we will see shortly, and C1 and C2, both with three classes. We have to then specify x1 as categorical in addition to the latent class indicators, because it's going to be yet another perfect indicator. Slide 61 then, and we have the overall model. Since it's regular LTA, we have C2 on C1, and we also regress both C2 and C1 on C. So they can be different as a function of the group. And here's a new feature. We have not only model C1 and model C2, but also model C1 with two classes. And we say then that that x1 variable It is categorical, binary, and we're saying that its threshold is either plus 15 or minus 15 fixed. So very high or very low. Very high threshold means that it's hard to surpass it, which means that the probability that x1 is 0, the lowest category, is 1. And it is that way for C class 1. And here we have a very low threshold, which means it's very easy to surpass it. So x1 is equal to 1 with probability 1 for C class 2. So x1 defines the C classes, the two C classes, by an observed perfect indicator. The rest is the same then, model C1 and model C2 with its measurement invariance. Slide 62, we turn to multiple group, multi-step LTA. So we do multi-step now instead of regular LTA. So here's the first step of BCH. Same data set, and we have 3 latent class variables as before, and we want to save the distal outcomes for a second step analysis. And you do not have C on C or C2 on C, C to C1 on C. Those are both commented out. And here we define the perfect indicator, and here we have the measurement invariance. And since we want to do BCH, we save BCH weights. Slide 63 then, last step of BCH. Here is the data set, here are the variables in the data set, and we're going to use Y1 through Y3 here, and training data. And categorical is Y1 and Y2, and Y3 is continuous. X1 is not included here now on the indicator list. And we have C on C here in the overall model, where the Y thresholds and means vary across all the 18 combinations as the default. So 3 times 3 is 9, times 2 is 18, 18 combination classes. And then, slide 64, we get a strong sign of BCH failure. And it turns out it's an error for relating to the middle category of the ordinal distal outcome Y2. So here, for instance, in class pattern 113, variable Y2 has a negative frequency for category 2. So here's one of those negative frequency problems of BCH that I mentioned on a previous slide. You know, we had negative variances, negative frequencies, possibilities. So and we have a couple of those problems for Y2 in category 2. Y2 is ordinal with 3 category. This is the middle category. So we have a problem here, BCH failure. So on slide 65, we instead turn to two-step. On previous slides, we had BCH failure, but now we turn to two-step as an alternative. On slide 65, we have then, in the last step of two-step, C on C statements here. Oh, we should also note that the categorical list then includes the indicators and X1 and Y1, Y2, whereas Y3 was continuous. So down here, to the bottom left, we have the perfect indicator specification. On the right, we have the fixed measurement parameters for time point 1 that we get from the first step analysis, asking for S values. Next slide, we continue with C2, and we see that we have the same values for C1 and C2 because of the equalities. And then we get results here that we're going to focus on slide 68. We're going to take a look at the threshold estimates for the distal ordinal Y2 variable, where we had that problem with the middle category. And we're going to compare two-step and BCH for this specific latent class pattern 113 that was first indicated as problematic on a previous slide. So the thresholds then for Y2, since Y2 has 3 categories, it has 2 thresholds. For two-step, we see that the thresholds are the same, and therefore leaving no room for anybody in between of the two thresholds. You have people below the first threshold, you have people above the first threshold, below the second, and you have people above the second threshold. Those are the three observed categories for the y2 variable. But when the thresholds are the same, they collide, and then nobody is in that middle category. And that's okay for two-step. They collide, but it doesn't hurt the estimation. It doesn't come to a halt. And it just reflects that nobody is in the middle y2 category for latent class pattern 113. It's not an empty latent class pattern. There are people there. They just have those people who are in there in that latent class pattern just happen to have nobody in the middle category for y2. Now for BCH, however, those thresholds, look at them. Second threshold is lower than the first. That doesn't make sense. Thresholds should be increasing in value. At most, they should be the same. They can be the same, but otherwise they should not be lower for the second threshold. So BCH has a problem. It's not okay to have those kinds of thresholds, and you get a BCH failure due to negative frequency, like we saw. But the two-step solution is quite usable. Now there's also a little twist here. You can change the y2 ordinal to a nominal variable to get BCH results if you insist on that. And it says here nominal y2, it should say nominal equals y2 here. So that's another alternative if you don't like the two-step results. But that's more of a curiosity. We now turn to RI-LTA, namely random intercept LTA, with an emphasis on the multi-step aspect of that. Slide 70 shows an example of RI-LTA with 3 time points, C1, C2, and C3, where we have distal outcomes Y influenced by the last time point, the latent class variable C3. The new feature here is that we have a continuous latent variable F, which we think of as a latent trait or a random intercept. It's a time invariant variable varying across subjects, so it is a between subject construct. Each indicator is influenced by this trait, and the remainder in the indicator is influenced by the latent class variable, where the latent class variable captures the within subject variation across time. So that's similar to random intercept cross-like panel modeling, RI-CLPM. The indicators at a certain time point have different loadings on the trait factor, and those loadings are held equal across time. So U1 loading is equal to U7 equal to U13, etc. This means that for each indicator, the correlation due to the trait is constant over time, which is the hallmark of a random intercept factor. This factor F can also be influenced by the X covariates. Both are time invariant, varying between persons. The X is vary between persons, and so does the F factor. We didn't draw those arrows because it made the picture look messy. This is described in the paper from 2022 in Psychological Methods, and also in Webtalk 1, where I go through several different data sets to show that RI-LTA often fits data better than regular LTA. I should also say that 3 time points is the minimum for RI-LTA. You can fit models for 2 time points, but you would need very large sample sizes, like 4,000 or 5,000, so it's not practical. Now turning to multi-step approaches, in this case the measurement model is this whole upper part of the model. All time points including F and including C on C for the latent class variables. So in this case, you cannot estimate time-specific LCAs because you also have that influence from the factor F. So, for instance, for BCH weights, you cannot do time-specific LCAs to create the product of the weights. So you would have to compute the weights for all time points together. And in fact, this also makes three-step awkward, where load just must be computed manually. We're going to take a look at BCH and two-step approaches for RI-LTA. Now, regarding multi-step approaches to RI-LTA, relatively little has been done to date. We have WebNote 21, where TMR did some simulations for both covariates and distal outcomes. For covariates, he found that two-step does better than BCH. And for distal outcomes, he found that BCH does better than two-step when distals are non-normal within class. So that issue comes back that we discussed before. Now we're going to focus on multi-step RI-LTA with distal outcomes, so only distal outcomes, no axis for simplicity. And they are normal within class as per how we generated the data. And we're going to look at BCH and two-step. On slide 72 then you have the input for RI-LTA, first step of BCH. So you have a new data set here with the 18 indicators. And we have 3 Y's. We also have X, but we're going to ignore that for now. And in the first step, we use the latent class indicators, the 18 of them, and they're a binary. And we have 3 latent class variables. And we want to save the Y's, the distal outcomes Y, for the second last step of BCH. And what's new here then is that we have to have an algorithm equals integration statement in the analysis command. And that's because we're defining this factor F, this continuous latent variable, measured by the indicators at each of the 3 time points. And here's how we hold the loadings equal across time by these labels. And we use an asterisk here for the first set to free up U1, which would otherwise be fixed to 1 as the default. Instead, we set the metric in F. The variance of F is 1, set the mean to 0. And in BCH, for RI-LTA, we recommend that you do have C on C. You do include C on C, so C2 on C1 and C3 on C2. And that's discussed in, that's per analysis in WebNote 21. The rest is similar then. You have model C1, model C2, and on the next slide, model C3, where you have measurement invariance across time. Going to the next slide, continuing here for the third latent class variable. And then you save the BCH weights, and we put that in a new data file. Well, here's the last step of BCH. You have this new data set, and we're going to have use variables Y1 through Y3 here. That's all we work with for BCH. And the first 2 are categorical. And we have the training statement here. And since it's 3 variables, three latent class variables with 3 categories each, we have 27 weights. 3 times 3 times 3, BCH. And look at this now. We don't have any F by U statement here because the U's are not included in the model, as you see on the use variable list. The information from the use is carried by the training variables. So no F by U, and therefore no algorithm equals integration is needed. You have starts at equals 0 as usual. And you have C on C here in the model. And now for model C3, last time point, you allow the thresholds and the mean for Y3 to be different across the classes. So having C3 influence Y. Slide 75, we turn to the first step of two-step. And here, as often with two-step, you can go back to the original data because there's no save data of interest really. You don't save cprobs, you don't save BCH weights. So again, first step, you have the 18 latent class indicators, 3 latent class variables, and you have algorithm equals integration because you have F by U, and as we recommend, you have C on C. For model C1, C2, and C3, you have measurement invariance here. And this starting value can be ignored, left over from a simulation, but you have S values here. Turning to slide 76, we look at the last step of two-step, where again we start from the original data. And the use variable list is then including not only the distal outcomes but also the indicators, the 18 indicators, because we fix the measurement parameters of those indicators. So we need algorithm equals integration again, and from the saved S values at the in the output of the first step of two-step, you get this list of variables, and you get the C information from the first step, also fixed, and the F by fixed values here. And on slide 78, you get the fixed measurement parameters for the U indicators for model C1, model C2, and on slide 79, model C3. And here for model C3, you see the distal outcomes coming into the picture, the thresholds and the mean for the Y1, Y2, and Y3, and continuing to slide 80 for the last class of C3. Now we come to the last topic of Webtalk 10, namely LCA at 2 time points. So LCA at 2 time points looks like LTA and has a lot of similarities with it. And we're going to look at the relationship between the two. So we have 2 time points, 6 indicators at each of the 2 time points. But the 2 time points can have different latent class constructs, dealing with totally different things, and different types of latent class indicators, and different numbers of them too, although they're the same in the picture. And we can have different number of latent classes at the 2 time points. In this case, since it's different types of variables and different latent class constructs, it does not make sense to include a random intercept at the top. So RI-LTA wouldn't be relevant for this situation. The latent trait addition would not be relevant. We're interested still, like in LTA, of predicting C2 classes from C1 classes. And we have the multi-step desire to not have time point 2 indicators influence the time point 1 class formation, and vice versa. So you can think of this whole thing here, the latent class variable out here, latent class model out here, as a distal outcome part of the model, where the first step relates to the first time point measurements. We're going to talk about the BCH multi-step approach inspired by LTA, where the first step is going to have no measurement invariance, because we are talking about different types of latent class constructs and different types of latent class indicators. Measurement invariance would not make sense. But like LTA, the first step is going to have no C2 on C1. In the last step then, what is the last step? Well, we're going to see that the last step has no observed variables. It's interesting. And includes C2 on C1, nevertheless. So why no observed variables? Why not U7 through U12? Well, let's see. Slide 83 shows the first step of BCH for this LCA at 2 time points. So it's the familiar data set up here. And now part of this approach is for the use variable list to include all 12 indicators. So indicators from both time 1 and time 2. So we have 2 latent class variables. And in the overall part of the model, we do not have C2 on C1, which makes it possible to create BCH weights that are estimated via independent LCAs for the 2 time points. We see here on the right that we have no measurement invariance imposed. So no measurement invariance together with no C2 on C1 creates the BCH weights in line with the first step of LTA. So all 12 variables are estimated or handled in the first step. Slide 84 then. The last step of BCH, we have the BCH data set, and we have a names list, the indicators, all 12 of them, and the 9 weight variables, 3 times 3. Now we're going to say use variables equals the weights. If we didn't have any use variable list at all, the model analysis, the analysis of the model would include all of these variables, which we don't want. But if you say use variables equals W1 through W9, then those get dropped off and are not used in the model explicitly, but only are used for the training statement down here. So it's a little trick. So none of the observed variables play into the second step here. Instead, all of the information is summarized by the training variables, the 9 training variables. And since it's the second step, we have starts equals 0, and then we do C2 on C1 here to get the information of how C1 influences C2 for LCA at 2 time points. And that's the end of Webtalk 10. We have an appendix here where we show how to do the Monte Carlo generation of the LTA dataset, LTA distal N2K. And I'm not going to go through that. It's created in a similar way with missing data on X's and on Y's as we did for the Webtalk 8 data generation. And it continues here, and then we have some references at the end. Thanks for listening.